Okay, ladies and gentlemen, welcome to the ICE technical meeting, strategy, vision, and the practical application of the principle of effective stress. This event is brought to you by the Institution of Civil Engineers. My name is Melvin. I am from ICE Student Chapter, Binus University, and it is a pleasure to act as your master ceremony in this event. Before we start, allow me to read the rundown of our event this evening. First, I will be reading the rules of the webinar. After that, the event will be guided by the representative of ICE-JLA localization, Phil Woodmansey, as our moderator to start the presentation of our featured speaker, Stephen Christian, and later will be followed by the main speaker, Laurie Wesley. The event will then continue with a Q&A session. Now, ladies and gentlemen, for your own convenience, please pay attention to the following rules. For online attendees, you can ask your question to the speaker by pressing the raise hand feature located at the bottom of the screen. For those who attend on site at Kemang, you can later raise your hand and the moderator will let you ask the question. The question should be in English. You can raise your question after the presentation of the speaker. Now, I would like to invite the representative of ICE-JLA Association, Phil Woodmansey, to give his opening remarks and also guided this webinar onwards. To Phil Woodmansey, the time is yours.
Okay, thank you, Melvin, and good evening, everyone, and welcome to our event tonight. Tonight's topic is geotechnical. So for those, and it's a very important topic, it's based around the principle of effective stress, which is just about the most important topic in geotechnical engineering. In our field, we borrowed most principles from other parts of engineering, but effective stress is actually something that we created ourselves. And I'm pleased to say that the speaker tonight was very much part of that original story. So also in keeping with what we're trying to do this year, we're also inviting students to come and co-present with our main speaker. And so tonight I'm very happy to welcome from Venus, Stephen Christian, who will be our main speaker, and they'll be talking about vacuum consolidation. Now, this is an academic case study which was very successful. They won 2 national competitions with it. They had the first prize in Geosindo competition, which is a national event, and they were 4th in the ITS competition, also a national event. So these guys have done extremely well, very successful, assisted, of course, by their professor at university, Dr. Anthony, who's also here tonight. So welcome to you guys. And so what we'll do tonight is we'll allow the students to give their presentation on their winning competition first. And then I'll let Mike introduce Laurie in about 15 minutes or so. So, Stephen, if you'd like to come forward, the show's yours.
The slide. Am I going to control the slide?
Yeah.
Okay. Yes. Iya, ya, sudah dipakai.
Dari sini.
Alright. Okay. Iya. This. This. Okay, good evening, everyone. My name is Stephen Christian, and now I will. All right. Okay, so before I start the presentation, for a little background, so this presentation is actually from a competition that me and my team have participated in last year, where we end up in the first place for this design. And then, so before I start the presentation, I would like to introduce my teammates first, who also here with us, Sandy and Randy. And then, other than that, I would like also to mention our supervisor who teach us a lot and lead us to the victory, Mr. Anthony Gura, who is also here with us. Okay, so the title for this presentation is vacuum preloading with additional fuel at a coal stockyard. So actually, in this design, we are asked to design a ground improvement method on a soft soil where we want to build a coal stockyard. So we have to use at least one geosynthetic product in the design, and then in the end we choose vacuum preloading with additional fuel method. Okay, so for the introduction, the project location is at Tanjung Enim, South Sumatera. Tanjung Enim at Tanjung Enim, South Sumatra, where the area of the improvement house it is 200 by 100 meters, and then they give us 3 boreholes with the MSVT value and some undisturbed sample until the depth of 17 meters. And then other than that, they also give us the disturbed sample. And then for the project requirements itself, there are some of them. First, we want to build an embankment of 2 meters, so the design level is 2 meters, and then the whole stockpile itself will be 10 meters high. So the total load from these two is going to be about 160 kilopascals, or maybe it's equals to 16-story buildings. And then in the existing condition, it's already submerged in water as deep as 1 meter. And then in the flood condition, it can reach about 1.5 meter. And then there are also some other requirements such as the factor of safety. In the static condition, it has to be at least 1.5. And in the seismic condition, it has to be at least 1.1. Other than that, after we build the stockpile, the settlement limit is only 20 centimeters, which I think is the most challenging part in this competition. So for the design steps, first we also we are going to process the soil data, where as you can see in the middle, it's the MSVT value, and then we idealize and we take 3 layers of soil. Where as you can see in the first layer, the MSVT value is very low, which means the consistency of the soil is very strong. And then the soil type for this area is clay. And then back in this slide, what I want to really tell you is that we found the NSPD value is not really aligned with the laboratory data. As you can see in the second layer, we take that the NSPD value is 8, which is classified as medium clay. But if we see the compression index and the void ratio is still quite high, which tells us it's still very soft. So in the end, we are we design 2 different scenarios. The first one is with the laboratory data, which 0.9 compression index, and then the other one is from liquid limit correlation, which is has a lower compression index value, and we want to show that how can how can soil data really affect our design in the end. And next, we model the design is in the final element program, which is Fluxys. First, of course, we have to define the soil layer, and then we want to build the working platform, where we also lay out some geotextile nonwoven as a separation, and then we can install the prefabricated vertical drain to accelerate the consolidation times. And then we can also assign the vacuum payload, which in the ideal condition you can reach about 80 kilopascal. And then this is the compensating embankment because as we know, after we load the soil, the soil below will be settled. So there will be some settlement that we have to compensate at the filling. And then this is the payload. Okay, so maybe before I continue, maybe some of you already know what payload is, but for you who may not know, I will just explain it a little bit. So payload means what it literally says. So we want to load the soil before we build the permanent structure. Why? Because it's actually really relates with the behavior of the soil itself. But the lot itself is temporary, so we will remove it at some point, and then we can build our permanent structure. So how this method works is actually correlates with the consolidation of the soil, but I will not really go deep into that because the time limit. So I will just show you in the modular result with which I think you can really see clearly how the payload affect the design. First, this is the okay. So as you can see in the upper part, it's the wall. In the first region, it's where we assign the payload and the vacuum, and then at the part where it's a straight line, it's the consolidation, which in this case we assign it for 3 months. And then after the consolidation is already done, we can non-activate the vacuum and cut the embankment. After that, we can just build the cold software, and we can see in the settlement. Okay. As you can see in the first part, the settlement is really high. It after the consolidation is already done, it reached about 5 meters. But after we remove, it will rebound a bit, and then after we build the stockpile, the settlement will just is a little. As you can see, if you compare it to that part, it's really low. So it shows how payload really works to reduce our settlement in the permanent load. Other than that, from this method, we know that we also do some consolidation process, and then consolidation is going to also increase our subgrade stability. Why? Because at the consolidation process, it will the excess motor pressure will be dissipated. Hence, it will increase our effective stress. Because our effective stress increase, our soil strength will also increase, which I think that topic will be discussed more in the next session. So as we can see, after we build the whole soil, the settlement is only 14.1 centimeters. All right, where it okay. This is for another cross section because the area is 200 by 100 meters, so we model it into two different cross sections because we just model it as a two-dimensional cross section. So this is for another cross section, and then this is for the second scenarios, which where we are using the lower compression index value. Okay, this is for the next cross section. So if we compare the two different scenarios, of course, we can see that the settlement in the lower compression index will be lower. Other than that, the need of the preload height is also smaller. So the needs of the field itself will be much smaller. Other than that, we have to remember that because the soil will settle, and we have to compensate it somehow, the compensating embankment in the lower compression index will be also smaller. So this shows how our soil data really affect our design, and then it shows the importance of it. Other than that, we also give some alternative option, which I think this is our unique selling point that differentiates us from the other team. In the alternative option, we are also proposed to use water as replacement of the soil fill. So it can be like this, but we only model it with the scenarios with the compression index of 0.3. But what's the consideration? Why we want to do this? So there are some considerations that you can take why we have to do this. First, if the fill is hard to find, as you know before, the need of preload height is quite a lot. So if the soil for the field is hard to find, it's going to cost a lot to just move the soil into the area. Other than that, as we know that in the existing condition, the area is already submerged in water. Other than that, we can also use the water from the vacuum preloading process because it will produce a lot of water, and then we can use it as a surcharge. Okay. Other than that, of course, filling water is a lot faster than we just using soil embankment, because in the soil embankment we have to mobilize it and then we have to compact it, so it will take a long time. Other than that, we can also use this as a temporary fish pond. But in this there are maybe some other considerations that you have to take if you want to use it as a temporary fish pond, because for example, like who will really manage this thing? I don't know, or if they really can manage it if they have no experience before. But I think this is really unique idea, isn't it? Because the consolidation time is it takes quite a long time, so we actually can let the fish grow actually. Okay. So this is the real case from Geotech Indo, where they use seawater as the surcharge for the preloading. So for the conclusion of this presentation, first, based on the soil test data, we can see that there is salt clay in the subgrade soil. And then the recommendation for the improvement method is the combination of soil and vacuum preloading, and the consolidation process is accelerated by using PVD. The PVD is installed in square pattern with spacing of 1.8 meter and the depth of 17 meters. And then the analysis done into scenarios where the higher CC scenarios need higher preloads to meet the design criteria. And then it also needs additional reinforcement for the stability of the environment. And then overall, using water lock is better than using solvent as long as the water resource is not hard to find. Okay, that's all from me. Thank you.
Thanks, Stephen. That was excellent. Really clear, concise presentation. So we'll now get over onto the main event. Okay. Again. Okay. Yeah, thanks, Stephen. That was excellent. Very clear, concise presentation. So we'll now move on to the main event for this evening, and I'll let Mike Doby, who's a regional manager of ICE, to introduce our main speaker. Thanks.
Thanks very much, Bill. Welcome from me to everybody who's come this evening. It's very nice to see everybody coming into our live meetings again. I hope you're getting used to this idea, because we'd like to have more and more people coming. But I have a really pleasant duty. I have to introduce our speaker tonight, our main speaker. First of all, I'd like to say, before I talk about our main speaker, Stephen, that was a very good presentation. Very good indeed. And for those in the audience and listening online, there will be a chance to ask questions. But because Laurie, you can probably see Laurie there on the screen. Don't forget, Laurie lives in Auckland, New Zealand, which means he's 5 hours ahead of us. So look at your watch and you'll work out that he's having to stay up a bit late tonight. But let me tell you a few things about Laurie, because I've been fortunate to know Laurie now for almost 30 years. And it's been a very rewarding interaction we've had many times in a number of places. So a few words about Laurie. Laurie is he said he's a retired geotechnical engineer, but I don't believe, Laurie, you're ever going to really retire from this. Geotechnical engineering will always be going around in your head in some way or other. Laurie's early career brought him to Indonesia, twice, in fact. He had 2 spells here, helping to establish testing and various things in the public works department here in Bandung, which he might mention later on, I'm not sure. He also then spent time in the UK twice to do both a master's degree and his PhD at Imperial College. And of course, that was where he became, if you like, he was a student of Professor Bishop. And you'll be hearing more about that also, I'm sure, when Laurie speaks to us. He then returned to New Zealand. He worked for a consulting company for a while, and then the rest of his career was as an academic at the University of Auckland. In fact, that's where he was when I first met him. So great memories of that, Laurie. Laurie has authored many papers. There are many published papers with his name. In particular, there was an early one in geotechnique about soils of volcanic origin. And that's still a really interesting paper, but of course, many of his more recent works have built up on that. So more recently, Laurie has also written a number of books, and in particular, the one about the residual and alluvial soils is an extremely interesting book, because it looks at both origins of soils together, and it's certainly a really interesting book and a lot of extremely important information. Now that one was translated into Bahasa Indonesia, and he also translated another book, Mechanica Tanah, into Bahasa Indonesia, which was coming from his early days here, and then later on he's updated it. So Laurie's been very busy
creating publications. And I think Indonesian engineers can take advantage of this because these are two excellent references, which I hope you all, most of you anyhow, have a copy of. If not, please get hold of it because it's a very, very useful book. So Laurie, sorry, I'm going to get you busy in a minute, Laurie, presenting to us, but I just wanted to make a few comments about the topic tonight. As you know, the topic is about Terzaghi, Bishop, and the principle of effective stress, which of course is an underlying and fundamental principle for our geotechnical engineering, our soil mechanics that we make use of in our design work as civil engineers. So I'd just like to say a few things. Now, first of all, I thought, is there any connection between Terzaghi and Indonesia? In fact, there is a very simple one. In fact, he was born in 1883, which is the year when Krakatau erupted. So it's not a very strong connection, but I thought you might be interested to hear that. But what I was interested to explore for a couple of minutes, and I think Laurie will give more information about this, is the relationship between the two men, Terzaghi and Bishop. What you'll find out is that they actually had an age difference of 37 years, which is quite a lot. And so you wonder, how did they interact? Did they interact? So I thought I'd just put a few bits of information for you here. So almost certainly the first time they were together in the same place was at the second International Conference for Soil Mechanics and Foundation Engineering, which was held in the Netherlands in 1948. So for you young engineers here, just imagine this. You're a 28-year-old, you haven't got your PhD yet, and you are listening to presentations from the president of the International Society, who's 65 years old. So how do you think about that as a young engineer? So just think about that, especially you students perhaps, because that was the situation that Bishop found himself in. So Bishop did publish 2 papers in that international conference. They're not very advanced papers. One's about shear box testing. However, as we move further on, Bishop and Terzaghi are both present at the next 2 international conferences, which of course are the 3rd and 4th, 1953 and 1957. And by the time of 1957, Bishop is publishing what I might call much more advanced papers, where especially his information, his ideas about measuring pore pressure and understanding how pore pressure influences the behavior, especially of clays, was becoming much more advanced. So did they actually get down together and have a discussion about it? I'm not sure I know. Maybe Laurie can give some ideas about that, but I'm fascinated to think about how they may have interacted, because their characters, as I'm sure Laurie will tell you in a minute, were very different. But they both have a really important place in the development of our topic of soil mechanics and geotechnical engineering. By the time we get to the 5th International Conference in 1961, Terzaghi doesn't attend it. I think by that time, maybe he's not in a condition to travel or attend these things. So only Bishop was there. And just one last thing to mention, quite interesting, is that Terzaghi was the president of the International Society for 21 years, which is a very long time. Of course, the Second World War came in the middle of that, which interrupted it a bit, but in 1957, he gave up that mantle and he handed over to Skempton. So I just thought a little bit of background, because I've done a bit of research in this, but nothing like the research that Laurie has done. So for those of you who don't know it, Laurie has written an incredibly good book about Bishop. And if you want to understand the development of soil mechanics, especially in the UK, you need to read that book. It's extremely nicely written. It's not particularly long, but the content is excellent. So Laurie, I've kept you up for far too long now. So I'm going to stop talking because my wife is giving me signals from the back there. And please, Laurie, could you take over before I say something completely stupid? So anyhow, welcome to Indonesia and to Jakarta again, Laurie. This is, I think, the 5th time you've spoken to the ICE here. And we're really looking forward to hearing your presentation tonight. Thank you, Laurie.
Thank you, Mike. Now I need just to click on something to bring up my PowerPoint. Is that right?
Yeah, that's right. Yeah. Hang on a minute. It's not quite there yet. You need to share your screen.
I should open my PowerPoint first, should I?
Can do it, okay.
But now I can't see. Sorry. I pushed the wrong button there. Hang on. I can see my presentation, but I can't see the share button at the bottom here. Maybe if I now I can see the share one now. In green, I'll click on the share button, which I just did, and another click here.
Coming up. Yes, now press the presentation mode and maximize it.
Yeah, I'm just about to do that.
Yes, it's perfect, Laurie. We can see it very clearly indeed. Thank you very much.
Thank you, Mike, and thank you everybody for coming along to listen. I would dearly like to be in Jakarta at the moment because it's very wet and very cold here in Auckland. I could well do with a short stay amongst the hot weather. I just want to add something to what Mike said about Tertsagi and Indonesia. If you go up to Bandung and head down to Pengalingan and up into the hills there's a dam called the Cipanunjang Dam, which the Dutch built in 1927 or 1928. Now, in the 1930s or the 1940s, the British were involved in building a dam in Kenya on red clay, and they had reservations about whether the red clay was suitable for building a dam. It didn't seem to behave like other soils did. So they called in Tertsagi to get his opinion, and Tertsagi did a literature survey to find out what other dams had been built in similar material. And he came across a paper written by the Dutch. He must have got it translated into English, and it gives an account of the construction of the Cipanunjang Dam in Bandung. It's about 35 meters high, built entirely of high allophane content clays, and it's been performing totally satisfactorily unto this day. But you'll find in Tertsagi's paper, which is in the Institution of Civil Engineers paper, an account by Bishop of the 3 other dams that he tracked down and got information from that gave him the confidence to recommend that they should go ahead with the Sasamura Dam with the similar red clay there. So let's get back to this. The first part is a little bit about the history, and then I'll move a bit more on to how you apply the principle of effective stress in practice. So I'll just keep moving on here. Now, I can't quite see the top of mine here. I might just have to move a bar up or something. Let me have a look. Ah, yeah, that's better. Yeah. Now, as I've written there, Carl Tertsagi is the undisputed founder, the father of modern soil mechanics. I should just explain too, the reason that soil mechanics grew very late in the day was because the people who were studying it knew how concrete behaved, they knew how wood behaved, they knew how steel behaved, and they were expecting similar behavior from soil, but it never seemed to work. And it wasn't until Tertsagi pointed out the fact that when you apply stress to soil, that load is going to be shared between either the soil skeleton and the water in the pore space, or one on its own or one on the other way. But whatever analysis you're attempting to do, you have to understand that when you apply a stress or a load to soil, the load is shared, or is likely to be shared between the soil particles and the soil. And that was Tertsagi's great contribution, really, was finding that out and putting it into writing in his earliest book and his later book. So his first book was in 1925, and that's generally regarded as the start of modern soil mechanics, written in German. Tertsagi was born in 1883 in Prague, but he was an Austrian, and his father was an officer in the Austrian army stationed at Prague at that time. He started off with a degree in mechanical engineering, but became interested in geology and eventually settled for a career as a civil engineer. His work career involved times in Vienna, Istanbul, America, back to Vienna, and then finally he settled in America. Well, he left Germany at the time of the rise of the Nazis, and I don't think he went back to Germany after the end of the war. He was a very keen geologist, and he always emphasized the importance of geology for engineers. And this is what I've just said, but I'll read it again. Terzaghi discovered and explained that when a force, pressure, or stress is applied to a soil, it will normally be resisted by both the soil particles and the water that occupies the space between the particles. And he expressed that principle in the very simple equation that you're quite familiar with there, that the effective stress is what is important, and it is the difference between the total stress and the pore pressure. Terzaghi maintained correctly that change in soil volume or strength only occurs as a result of a change in effective stress, not as a change in total stress. Terzaghi, in relation to the shear strength of soils, Terzaghi adopted the basis equation that Coulomb had put forward for the shear strength of soil as C equals C plus sigma tan phi. Coulomb's work was really entirely to do with dry sand. So in that sense, there is no mystery about the equation as it is. Coulomb assumed that the value of sigma was the direct normal stress on the soil and that the soil behaved like a dry sand. He was unaware of any issues influencing this assumption. Terzaghi recognized that the value of sigma could be either total or effective stress. He also understood the best way to investigate how soil responded to applied stresses was by undertaking trioxer tests. That's because he was able to control both the applied normal load or the confining load, as well as recording what was happening with the pore pressure. However, Terzaghi did not get as far as establishing a sound theoretical basis for applying the above equation and the results of trioxer tests to practical situations. This is where Bishop comes along. This is a quote from his book that was well known at the time, Theoretical Soil Mechanics. For these reasons, the data required for making a stability computation pertaining to clays can at present be obtained only by means of following a purely empirical procedure. You test the clay in the laboratory under conditions of pressure and drainage similar to those which would be in the field under shear failure. And we introduce the values of C and phi that you get from that into our equations. And then he states it is obvious that the success of this procedure depends chiefly on the degree to which the experimenter has succeeded in imitating the field conditions. So Terzaghi established the principle of effective stress, but he failed to arrive at a rigorous method for applying it to the analysis of stability situations. Now that book came out in 1943 with that statement. That was the year that Bishop began his career with the London Metropolitan Water Board. So what he had to read at the time was Terzaghi's book and the proceedings of the first international conference, and there were one or two other papers published in American journals, I believe. So the literature he had to read was very limited, and no doubt he studied. There's no doubt about that. He got himself up to speed with the literature very quickly, and he would have come across the statement of Terzaghi. So that must have been the seed that led him to spend most of his early years investigating the principle of effective stress and sorting out the ways in which it should be applied to practical situations in the field. I just made this point that Terzaghi's achievements were the result of unrelenting examination of how soils behave, primarily from careful observations in the field, but assisted by laboratory experiments. And then number two, development of theories to explain this behavior. Terzaghi's book, Theoretical Soil Mechanics, was, I've just listed the date, 1943, has been quite significant. Terzaghi's book, Theoretical Soil Mechanics, was published. Alan Bishop joined the Metropolitan Water Board, worked closely along with the soil mechanics group at the British Building Research Station. That was where Skempton had been employed there for the specific purpose of developing soil mechanics. And Bishop, in effect, was seconded or worked with the Building Research Station in the early years of his time with the Water Board. And that's Bishop on the right. And the photo on the left is that the Chingford Reservoir today, a very large slip occurred down in this bottom western or right-hand corner here. A massive slip occurred during its construction, which set it back by many years, and the investigation was very thorough into what caused it or what they could do about it. And they called Terzaghi over to report on it. And in fact, when I visited the London Metropolitan Automate, they gave me a copy of Terzaghi's report on the failure of the Chingford Dam and the investigations into it. It was all pretty straightforward. Common sense, really. Skempton's tribute to Bishop in the Bishop Obituary and Geotechnique. It's a very nice, it was an addition to Skinner, who wrote the real obituary when Bishop died. But this is what Skempton said. It was a great privilege and the best of good luck to be associated for nearly 40 years with one of the finest intellects in our subject. In no respect was his intellectual power seen more clearly than in his continued study of Terzaghi's principle of effective stress and its application to all branches of geotechnical engineering. His work in this field brought about a highly beneficial revolution in soil mechanics. Although reserved in a manner compatible with his Quaker faith, he appreciated a good sense of humor. He was loved and respected by his numerous students who came from all parts of the world. Through them and the strict but friendly criticism of his colleagues' work and his own important contributions, he exerted a unique influence. These are the important dates. There's the failure of the Chingford Dam here, and that's regarded generally as the birth of soil mechanics in Britain. The first international conference had been held earlier than that, 1936, and that was organized by Terzaghi, and he did it obviously with two objectives in first. One was to have the conference, but then secondly to introduce Terzi to a much wider audience that he was currently communicating with. So there's where Bishop starts his job, 1943, in the war years, and when Terzaghi's book Theoretical Soil Mechanics was published. In 1955, Bishop published his paper on his slip circle method of analysis. But the more important paper, where he settled the issue of how you apply the results of triaxial tests to stability estimates, was at that conference there. And I'll perhaps refer to it again later, but that settled out clearly exactly what the way the results should be used. Moving on. Yeah, I've already said that. Major slip in 1937. Bishop in 1943 joined a small soil mechanics group at the BRS, which was responsible for investigating the cause of the failure of the Chingford Reservoir. It also worked on modifications of the design of a second reservoir, taking account of lessons from the Chingford failure. And that's where Bishop really started to make his mark. It was in the design of earth embankments or earth dams, if you like, but the earth embankments that they used for creating storage lakes in London. So Bishop faced the issue left unresolved by Terzaghi, a rational way of using the results of triaxial tests for analyzing practical stability situations. Bishop was the ideal person to take up this channel for several reasons. He was a very practical man. When I was reading the Imperial College archives to write the Bishop biography, I came across a letter which Bishop had written to ICE as support for him gaining membership of it. And in his letter, he gives an account that he took the practical courses when he went to Cambridge University. And what he did there was a nice continuation of the work he had been doing in his own workshop at home. So he was obviously into workshops and that sort of thing from his early teenage years. So it was not exactly surprising that he was a brilliant designer of apparatus, because from an early years he'd had a workshop in which he made various things. His first job made him realize how important this issue of soil shear strength was for the safe design of reservoir embankments, and he was fascinated by Tsursagi's effective stress concept. Couldn't quite believe that it was as simple as that, and he went on for some time looking into the effect of particle area contacts and things like that. But in the end, he performed all the experiments that he wanted to make in order to be quite sure that it applied for all ranges of pressures. And Bishop had a very sharp mind, essentially for the development of theory, and he was able to design and construct whatever testing equipment was needed to sort out the issue he was addressing. And I think I now come on to having a visit to look at his first triaxial apparatus. A note on the Bishop method. Bishop is best known for his method of slip circle analysis. However, in the Bishop obituary by Angus Skinner, we find these words: theory and practice welded together by continually checking once against the other. This was the formula used so successfully by Bishop. So this gives us a much broader understanding of the term, the Bishop method. In other words, if the Bishop method had only applied for the method of slope stability that he analyzed, they probably would not have used that as the title of the biography that I wrote. But because the Bishop method was a very specific method, as Skinner outlined in his comments here, he worked on 3 fronts: the development of theory, the creation of laboratory equipment, and field observation. Now look here, I went there to have a look at Bishop's triaxial apparatus, and who should be standing right beside it? There he is. That wasn't quite the truth. Mike was very helpful to me while I was in London, and he took me to visit both the Bishop's first triaxial apparatus and the first dam that Bishop wrote. So many thanks for that, Mike. There was a great connection. Mike just happened to be in London when I was there reading the Bishop archives. Bishop's first triaxial apparatus, built between 1943 and 1946 at the Meadowhall. It was a very clever apparatus, or you may have heard the description of it that Mark Swen from Tensor gave a while back. The special features it got. He did a very nice presentation. One that he had the rotating bush at the top so that there was no friction between the ramrod that was going down, and a very clever system for doing mechanical recording of gaps. You could just see it down below there on the right at the bottom there. And I had to put this in because I did spend 3 years under Bishop doing a PhD. In fact, I went to Imperial College very determined. I wasn't going to design apparatus and use up most of the time of my PhD and not have any time left for doing experimental work. But I looked around at the equipment that they had there, and it was fairly clear to me the only way you're going to be doing what I had to do was controlled stress application, not controlled displacement, which is the usual way. And the only way you can do controlled stress application, at least in those days, was by a hydraulic system where you had somebody who could control the hydraulic pressures. So in the end, I had to design an apparatus, and I tried a few designs which I didn't like very much with the conventional way of applying a load from the top. And then I thought, well, maybe I should try and put a cell right down the bottom with a linear bearing going up and putting the sample on top of it. And I took it to Bishop, and he said, "Oh, yeah, it looks pretty good, Laurie. Just give me a night to have a look at it, and I'll let you know in the morning." In the morning, he came in and said, "Yeah, looks very good, Laurie. Draw it up and let's get one made and see if it works all right." So that's how that came into being. And when I produced some rather tidy results, Bishop, we wrote a joint paper and got it published in Geotechnique, and the thing has been manufactured ever since. And currently it is manufactured by GDS Instruments. It's been enlarged and altered in various ways, but it's still marketed as the Bishop Wesley triaxial cell. Yeah, now this is the paper that I was referring to that was published in 1960, The Relevance of the Triaxial Test to the Solution of Stability Problems. It was published, I've got the proceedings of this research conference, that it was published at held in Boulder, just outside of Colorado in 1960. That paper was undoubtedly Bishop's most important paper. even though he is best known for his method of slope stability analysis, published about 1954 or 55. You're probably quite familiar with it, but I'll just emphasize it. The question that the equations for volume change and soil shear strength are the following. You're quite familiar with all of those down there. Note that the equation sigma equal to C plus, sorry, whatever that one is, the shear strength equal to C plus sigma tan phi is meaningless without defining the type of stress for sigma and the way it is measured. This means that that equation as it is in terms of total stresses should not be used in soil mechanics. Bishop made that point very emphatically in that 1960 paper. They were, when I went to university, we were being taught things like C with a subject, with a suffix CU as from a consolidated undrained test. And then you'd have a phi from a D test and a phi from a U test. We taught that, but we didn't really leave. This was in the 1950s. So it was about the time that Bishop was sorting out the way to do triaxial tests and apply them. So it was only after I went to do the Imperial College one-year master's degree in 1964 that I really learned the basics of soil mechanics with respect to shear strength. The shear strength, I'll just explain this. The shear strength determined using the above equation is the strength in terms of effective stress. In other words, it establishes the parameters that you put into that formula. To use the equation, it is necessary to know the value of the soil parameters, C and phi, and the pore pressure U. And again, you probably know this. There was a second, that is the first and probably the most fundamental way of measuring the soil shear strength. But there is a second way of measuring the shear strength, that is by directly measuring it without allowing any change in its water content. For fully saturated soils, this means that no change in effective stress is occurring. If the sample is fully saturated and undrained, then the effective stress can't change. This strength is thus a constant, known as the undrained shear strength, not the cohesion. I know some people still use that term, but it's the undrained shear strength, usually denoted as CU or SU. Measuring SU can be done in several ways, and obviously, as you well know, is much easier than measuring the effective stress parameters C and phi. And you'll be familiar with that diagram. If you do a undrained test on fully saturated materials, you will get a set of circles like this. Regardless of how high you wind up your cell pressure, you're only going to get the same result. If, in fact, you did measure the pore pressure in each of those undrained tests, subtracted it from the total stress, you would all end up on that same one effective stress circle that you can see there in the faint blue there. So I've said that it's sometimes said in textbooks or maybe in lectures that this is a property of clays. It's got nothing to do with clays at all. The identical result will be provided on two conditions. The first one is that the soil sample is fully saturated, and second is the test that is undrained. The same result is obtained from clay or sand. However, the undrained strength SU is only of practical relevance in the case of clay. It is very rarely of relevance with regards to sand. Bishop established that the geotechnical engineer normally has the choice of two methods for analyzing the stability situation: an undrained or total stress analysis based on the undrained shear strength, SU. Skempton always called it a phi naught method, which was an easy way of sort of explaining it, whereas Bishop used the more correct technical term of being an undrained analysis or an undrained test. The analysis in terms of effective stresses, so that's the choice you've got: an undrained analysis based on the undrained shear strength, or an analysis in terms of effective stress based on the effective stress parameters C and phi. The latter, sort of for understandable reasons, just in contrast to an undrained test, is called a drained analysis. But this is not sensible at all. An analysis in terms of effective stress makes no assumption about whether the failure will be drained or undrained. And in fact, an undrained situation can be analysed in terms of effective stress. You just have to know what the pore pressure is. So calling it a drain analysis rather than an analysis in the terms of effective stresses is not sensible. Bishop also stated that for most stability situations, there are two cases to consider: the end of construction or immediate case. Stability in this case can be estimated using a total stress analysis based on the assumption that the clay is of very low permeability and the undrained strength does not change during construction. And then there's the long-term case. Bishop, of course, was thinking particularly of cuttings in England, cuttings in the very low permeability London clay, and their stability or lack thereof was an early focus of the geotechnical people in the early development of soil mechanics. Was why some of these cuttings failed after they'd been stable for 10 or 20 years, and it was a puzzle for many years just exactly what was going on there. But anyhow, this is what Bishop was talking about, the long-term case, which applies when sufficient time has passed for pore pressures to reach their equilibrium steady state. Stability in this case is normally determined using an effective stress analysis. But there are cases where a total stress analysis may be appropriate, taking into account the change in the undrained strength that may have occurred. But I think we would probably all agree that for a long-term case in cuttings in low permeability clays, we need to do an effective stress analysis. And this is just to sum up, or in a very simple way, why you use undrained strength in one situation and an effective stress analysis in another. Say we've got a clay and we're doing something with it. The first thing we could do is to build a structure on it. If you do that, you obviously, as I said before, the load is taken either by the soil particles or the pore water. If it was a raft situation like this, initially it would be mostly taken by the pore water, because it would take quite a long time for the water to seep out, particularly in low permeability clays like London clay. So in that case, you're perfectly safe if you base your estimate of foundation pressure on the undrained shear strength. You're going to gain in strength with time, and your basic basis for your estimating variable capacity, in other words, using the undrained shear strength, is perfectly valid and is safe. But the opposite is the case when you make an excavation. If you remove all of this load from the soil below by excavation, then you're going to induce the reverse of what happens here. Here you would induce positive pore pressures. Here you will induce negative pore pressures, and the water will start to flow towards the excavation, and it does that, the soil will become steadily softer. So I think I know for estimating the long-term stability of slopes of this site, you've got little choice but to use an effective stress analysis. For made soil slopes, such as cut slopes in original ground or embankment slopes of compacted soil, it's generally necessary to make, as I probably already indicated, to make two estimates of stability: the situation at the end of construction, the long-term situation. The estimates are likely to be different because the pore pressure state will probably change with time and thus produce different values of safety factor. Just be clear on one thing: soil will behave in an undrained state in either of the following situations. Water is unable to flow in and out of the soil because all of the boundaries are impermeable, as for example, an undrained triaxial test, or when the soil permeability is very low and the loads or stresses applied fairly rapidly, as for example, when an excavation is made rapidly, or a storage tank is filled quickly with water. So in that case, in many clays, particularly clays with permeability as low as London clay, the soil will behave in an undrained fashion or an undrained state. And we will consider some practical situations. And the question, why do we use a total stress approach using the undrained strength in some situations and an effective stress approach using the effective stress parameters in other situations. I'm not sure if I haven't got the two slides the wrong way around, because I think I've already explained why those two ways of analyzing things are sometimes undrained and sometimes in terms of effective stresses. I think I've explained this. These are just examples of the sort of foundations or loads you may be putting onto it. A building will go on there pretty quickly. So in that case, you're quite safe to base your bearing capacity on the undrained strength. The same here, actually. This is a tank, and you can apply your load even quicker when you fill the tank up with water. In fact, on building tanks on soft clays, you often have to sail pretty close to the wind with relation to bearing capacity, simply because you often have to build your tanks in areas close to ports and places like that where you've got fairly soft alluvial clays. So one of the good things you can do is you just fill your tank up the third fill, and then record the settlements, and if they're looking satisfactory, you steadily keep it on up, allowing some consolidation to occur as you apply the load. And again, with this is another case when you're building a compacted abutment on soft clay under here. I'm just checking what I wrote on the left here, that you could do the same. You could do the same with this, but not with the material underneath if it's a soft clay. In other words, it's of a soft clay here, you're going to have to do a slip circle analysis that passes through the compacted material here. This will possibly, you're most likely to be using a fairly granular material here. So you're going to have to make some assumption about the phi value for it and use the undrained streak down this part below here. So there are times where you have to rather mix the two methods. Now, you're quite familiar with this, so I don't need to emphasize it, but the analysis yeah, the stability of natural slopes is always done using an effective stress analysis. I should make it very clear, actually, and I haven't done in this presentation. My view is with natural slopes, particularly in residual soils, the variability of the material is so great that you're really wasting your time trying to apply slip circle analysis or any analytical methods to them. Your best guide is firstly just visual inspection of the slope to check out what it looks like. If it's got odd bits and pieces all through it, you can tell whether it's likely to have had slips in the past. But I've just been writing something about estimates of stability and the usefulness of analytical methods. And I looked up a couple of textbooks, Das and another one, Budu, I think. They make very clear statements in this regard, that the application of analytical methods to natural soils is fraught with many uncertainties because of the variability of the geology and the soil conditions. And Budu also makes a very similar statement, warning out that the application of analytical methods to natural hillsides is fraught with difficulty. So just always bear that in mind. And textbooks tend to teach these, well, as any textbook would, the ways of doing analytical analysis of slopes. And of course, Bishop was involved with earth embankments and earth design, and that's a totally different situation. The designer has control of his material and can make sure that the material that goes in is uniform, and he will use proper methods to measure the shear strength parameters, and the pore pressures will know by the seepage states created when the reservoir is filled. So that's a very different situation. There's no real uncertainty about the value of the parameters you are using for making the analysis. But when it comes to natural slopes, particularly slopes in residual soils, there's a great deal of uncertainty. And my view, I used to teach my students that with respect to most natural slopes, 95% of your input is going to come from visual inspections and the understanding of the geology, occasionally from aerial photographs. You might only get about 5% from trying to do analytical analysis of it. But the advantages of an effective stress analysis are safety factor is much more reliable than from total stresses. The effective stresses enable the seepage state to be included as its influence on the safety factor is investigated, or you can investigate the influence of it by using an effective stress analysis. With regard to retaining walls, I think in general, a total stress analysis is likely to give an unsafe answer, although there is some debate about this. But certainly here, I think I would certainly do an effective stress analysis, even if it involved guessing the parameters of these materials here. It's quite interesting too. The way you can, this is the old way of building reinforced cantilever retaining walls. You cut back the slope, hoping it'll not slip by before you get the backfill in there, and then you fill it up behind there. So you've really got to do, the only way I think you can sensibly do an analysis in most situations is a Coulomb analysis using trial wedges, and you have to use trial wedges in both the backfill material and in the natural ground, because sometimes the natural ground may be quite weak, whereas your backfill will be quite strong. So you need to do a Coulomb analysis in terms of effective stresses in both materials. We make a lot of retaining walls for relatively small heights, just 2 or 3 meters, using pole walls, and they're particularly safe if you're likely to, or if you haven't got much space to cut back the excavation and use up your neighbor's properties. If you can't use a lot of space, you can drill holes and drop your, in our case, they're often timber poles. You can drop your timber poles in here, and then you can excavate and slot in horizontal planks behind here to retain this up here. But if it's clay, I think most of us are using bombs based on the undrained strength to get the retaining capacity of poles of that kind. Now, the tieback walls are particularly, or pop walls are particularly interesting, because the way of construction has a great influence on the load that's going to come to bear. I'll just concentrate on this here, where for example, you've put in these diaphragm walls, or even when you do this here, but if you put in these diaphragm walls, or you extra a little bit, or you put a floor in at the top, actually, on a lot of them, then you do excavation below, then you excavate down. When you put your floor in, it's probably not going to be providing any resistance to the earth pressure coming on here. But once you've excavated down to here, then obviously you're going to be transferring load to the top floor. As you excavate further on down here, down to here, and as you remove this one and excavate down to here, then the load is going to be taken by both of these floors here. And so you go on down to here. So you're not going to have a nice tidy triangular distribution of pressure in that situation because of the way it is built. And I think I haven't actually looked into this, but I did make a recommendation for a major excavation in KL one time, and I took some guess at what the envelope of pressure would be, but I allowed quite a substantial piece up at the top there. Here, I forgot I had this here, but a compacted embankment on soft clay. If the embankment is made of granular material, the analysis should use in the clay layer the undrained strength, and in the sand layer the effective stress friction angle. If the embankment is made of clay, then the analysis should use both materials. And if staged construction is necessary to allow time for consolidation. This last point isn't important, people. I mean, it is often necessary if you are building a a fairly thick embankment, or even placing a layer right across the site, it will always have edges. And if there's any need to allow for an increase in the undrained shear strength so that you can proceed with the next layer, I don't think it is wise or practical to rely on measurements of settlement as assurance that you have gained an increase in the undrained strength that you need to make the thing stable. I think you should, or you might even think that you're measuring the pore pressures and finding that the pore pressure dissipation is sufficient to ensure that you've got the gain in strength. My view is you should do a CP. The simplest thing to do would be to do a CP test down through here before you build the embankment, and then put your embankment in place, and then do another CP test. I know it's a bit inconvenient. You may have to get somebody to drill a hole through here to enable you to do your CP test, but in my view, only that way can you be sure that you've got the increase in undrained strength that you need in order to maintain the stability of the embankment. And I think I've put that note here: if stage construction is necessary to allow time for consolidation, the increase in undrained shear strength should be measured and used in the stability analysis. Yes. Moving on from that. Oh, a question. Should both methods give the same answer, i.e. the same safety factor when used in slope stability methods? If the answers are different, which gives the correct answer? I don't think it's a particularly useful question. The more appropriate question is to ask, what is the appropriate method to use, rather than those questions above. If you're using the appropriate method, then you will know that your safety factors are to be trusted, rather than trying to do it by one method and another method and trying to guess what one is going to give the right answer. Now, I just want to explain, as best I can, I will try, why they don't give the same answer, or they only, Bishop said they will give you the same answer if your safety factor is unity in the case of a vertical cutting. But let's just have a look here. This is in the field. We can imagine we're investigating the possible slip on a plane somewhere here. So we can do measurements in some way, and we know what the total stress is, and we know what the pore pressure is. So we can work along the bottom down here, and we can put in, we can do measurements to establish the Moore-Coulomb line, but we can put in here our total stress. We can put in our value of pore pressure, and then we can read this off here as the strength, and we can shoot this line up to here, and we can read that value off as the undrained strength, because we've done the test undrained, and we've measured the pore pressure. But that does not take account of the fact that when we do our triaxial test undrained, we are inevitably going to either raise the pore pressure or lower the pore pressure. In other words, to get the true undrained strength, we would have to know what the pore pressure change was during the test and put it in there, and we would come up with the true value of the undrained shear strength. So that is one attempt to explain why they give a different answer. At a more practical level, just think about doing an analysis of an embankment on a solid foundation here, and we end up with this red line. This is the circle that we have analyzed. Now, if we were using, and these graphs here are only graphs of the value of the shear strength. If we were doing an undrained analysis, I think we would probably use the same value all the way around. So that green line there would be the value of the undrained shear strength. If we were doing an effective stress analysis, because the effective stress down near the toe here is quite low and very low up here, then we would have very little strength here, and our line would come around like that. So clearly that's going to give us, or clearly we cannot expect that to give us the same answer. So that's another one of my attempts to explain why the two systems give you different answers. This is an exercise that I used to give my students, or if I was doing a course somewhere, I would get them to calculate the short-term, well, the short-term stability is zero because we've got a horizontal surface here, but to estimate the long-term stability, or to find out what sequence actually happens to the total stress and to the effective stress and to the pore pressure. We can work out the initial, we can make an assumption to get the initial pore pressure. We know the depth of the excavation, and we know that particularly if it is a level surface, the pore pressure will suddenly become negative by the value of that decrease in total stress. If you take the total stress off, then obviously you're going to, and it's undrained, you're going to induce a fall in the value of the pore pressure. So you can do an estimate of the situation at the end of construction just by drawing the new water table created. And I haven't shown it here, but the new water table will start up here because we're not taking any load off here. And it will end up way down here because we've taken all of that load off here. So it very easily gives you a basis on which to use to put your pore pressure into your analysis. But then you can take a guess at the long-term situation by putting in that water table there and feeding those pore pressures into your analysis and coming up with a change. And it's possible to plot the results in this way. This one at the top, this is looking at a particular element somewhere down at the bottom, somewhere down on the slip circle, just looking at a particular element. So this is looking at the total vertical stress. So we're unloading the soil quite quickly, and this is the end of construction line here, but we're assuming it's really quite quickly, although I've not drawn it quite like the way. And your total stress will come down by this value here, and the effective stress will stay the same during the time that you make the excavation. We've said it's an undrained analysis, so there's not going to be any change in effective stress. You're going to induce pore pressures equivalent to the effective stress that you apply. But from that point onwards, water is going to start to flow towards the cutting, and that means your pore pressures are rising and your effective stress is lowering. So coming down here we are, is what the pore pressure does. This line here is parallel to the line at the surface, and then the pore pressure starts to rise from that point onwards. And in keeping with that, your safety factor is going to fall when you make the cutting. That's just because of the change in the geometry. And from that point onwards, it will continue to decline further and eventually rise to some equilibrium values. So that line there was simply the mirror reflection of that line there, this being the change in safety factor and that being the change in pore pressure. And that what I just showed you is what people like Bishop would show in their lecture series, and totally relevant to London clay or the low permeability clays that you have in the UK. But if we're talking about residual soils, then actually you could well have pore pressure changes taking place as you make the excavation, because they're much more permeable than low permeability clays. So you're going to have something more like this, that you're going to make your excavation and you're not going to have a nice tidy pore pressure system. You're going to have a wavy line reflecting the seasons, the wet seasons and the dry seasons, and interspersed with those you're going to have sudden storm events which push the pore water up. I was just looking at the time, looking at the and in we know from our own experience, the seasonal changes in pore pressure, they've taken place for so long that they're not the current cause. If you're going to have failures in residual soils, or they'll almost invariably be as the result of short-term, very intense rainstorms. That's why I put these little bubbles in here. Those are the pore pressure rises. So coming down to here, we're looking at our effective stresses. Your pore pressure goes up, your effective stress suddenly drops, likely to cause a failure, and your safety factor will wander along down that. So what I've said here, short-term end of construction and long-term pore pressures and stability of cut slopes in low permeability soils and moderate to high permeability soils. Yeah, so the first one was the high permeability soils, and these ones are the low permeability. And I think I must be getting towards the close. Yes, that's I went to London in 1962, I think it was. It was to be a so-called expert witness in a contract dispute. It was in relation to a dam in an island just off Madagascar. There was a dispute there between the Italian contractors and the designers. So I went to London to be a so-called expert witness. And while I was there, I rang up Bishop just to say hello to him, and he said immediately, "Oh, Laurie, you probably know I'm a married man. I'm a married man now. I would like you very much to come and visit us and meet my wife." So I did that, and at the end of the visit, I took that picture. Going back a little while, I did my PhD between 72 and 75, and I and my mate Richard Pugh, we were the last two full-time students of Bishop's, because he had a bad heart, and he always was a rather anxious person. So the doctors had him on one of these pills to calm the nerves, but they didn't realize that if you took them in the way Bishop did for a long time, they started to produce the opposite effects of what they were supposed to cure. So Bishop was starting to have a mental breakdown just towards the end of the time when I finished my PhD. I wasn't aware of that, but when I heard later that he had had a breakdown, it did make me. And he took an interest in my work, but not as much as I would have expected him to do. It was rather interesting. I had my oral. Don't want to waste too much time. When I had my oral at the end of my PhD, my external examiner was Peter Roth from Cambridge, and Peter Roth is a very well known for his role in the creation of critical state soil mechanics, which Bishop didn't particularly admire. Anyhow, they were my two examiners, so I sat down to have this examination, and Bishop said a few things and then handed over to Peter Roth. And Peter Roth's first question was, how many technicians did you have, Laurie, to get all those tests done? And I said I had no technicians at all to help. I did all of the tests myself. And he looked very suspicious, and Bishop spoke up and said, well, no, Laurie's quite right. He did a brilliant design, and he's done far more tests than any other postgraduate student has ever done. In fact, nobody's ever going to do more tests than I did, because Bishop, but anyhow, to continue the interview, and then they asked me if there was anything I would like to ask them. So I asked them whether they were surprised at the low values of poisons ratio that I was getting from my triaxial tests. And they both looked at each other and looked at the air and tried to think of something to say, because obviously neither of them had read the thesis that far. And anyhow, that sort of brought the interview to an end, and I was invited to go and wait somewhere, which I did. And about an hour and a half later, they came out and told me I had my PhD, and we had some drinks and coffee with the other people who were around there, and then there was a bit of a chat, in the course of which Bishop said the problem Wesley had with his thesis was that neither of his examiners has actually read his thesis, which I thought was very honest, actually, because it was obviously they had. But Peter Wraith wasn't exactly pleased to let Bishop acknowledge that that was the case. Sadly, I got a, well, I'll go back one step too. About 19, I and both Richard Pugh, you see, he was doing the field work, I was doing the laboratory work, and we were writing papers with Bishop, separate papers, but we were working on 2 papers with Bishop. And we were writing our part, and then within a few years, we weren't getting any responses from Bishop. Then I got a letter from Peter Vaughan telling me that Peter Vaughan that Bishop had had a breakdown and they weren't sure when he would be coming back. And a little bit later again, I think about 1971 or something, I got another message from Peter Vaughan. He is, if any of you know him, Peter Vaughan was one of the finest people they had there. He was so very helpful to students, and he was wonderful to work with. He sent me another letter, and he gave me a little bit of small talk at the bottom. And at the bottom, he said, "You should probably sit down, Laurie, before you read the next page." So I read the next page, and he said, "You'll be surprised to learn that Bishop has A, got married, B, learnt to drive a car, and C, lost all interest in soil mechanics." So I knew then I was not going to get any help from Bishop in writing my work up, and in fact it remained unwritten until about 6 years ago I started to write it up, actually, and then I got sidetracked into doing a few other things, like writing the biography of Bishop. But I did get it written up, and along with the Bishop biography, I also put together a commemorative volume of Bishop's best papers, and Richard and I completed our papers, and we put them into a joint paper, and they got published in that publication. And although I say it myself, it's a very useful publication, because one of the reasons for it was that some of Bishop's best papers are not published, are published in rather obscure places. His paper in the ASC Specialty Conference has never been republished, and a lot of people don't have access to that. But two of his most significant papers were published in the, they call them they are the Proceedings of the Royal Society, but the name is a little bit grander than the Proceedings. I just forget exactly what it is, actually. So those papers are in that volume, along with some of his most interesting other papers. So that brings us to a conclusion, and I'm quite happy to answer questions or discussion if anybody wants to raise any points. So I'll hand back to Mike or whoever who can take over from this point onwards.
Laurie, thank you very much for covering a huge amount of information. Thank you. There's so much important fundamental background to the field of soil mechanics that you covered there, and finishing up with this incredible picture of Professor Bishop in his last few years. So we have a little bit of time. Anybody like to ask Laurie a question? You're going to have to somehow let me know if there's any question here. Is there any? Did he? Okay. Trevor, would you like to ask Laurie a question? Can he do it live? Okay. Hang on a minute, Trevor. Sorry, there is a question coming in for you, Laurie, from Trevor Symes, one of our long-term committee members here, who you probably met here before, actually, but he's currently in Timor-Leste, I think.
Right.
Hang on. Have you got him yet? Oh, okay, he hasn't quite come through to us yet, is that right? Has he written down the question? That seems like it's not going to happen. Okay, while we're trying to contact Trevor, Laurie, what do you think about the possibility of Bishop and Terzaghi actually interacting with each other and talking to each other and discussing anything? Do you think that ever happened?
No, I don't. And it's rather interesting that at the time of that conference in 1960, where Bishop and Buren published that key paper, Terzaghi was too sick to attend the conference, but they sent all of the papers to Terzaghi to comment on. And he comments on several of the American papers. And he also makes the observation that we don't seem to have answered a lot of the fundamental questions that arose at the time of the first conference. We don't seem to have answered the questions that arose then. And it seems we've still got a lot of work to do. He made statements to that effect. So it seems, I don't know whether deliberately or he didn't get around to it, he didn't bother to read Bishop and Buren's paper at all. And I can't quite, I mean, they were very different people, but Terzaghi really was pretty arrogant, and he was a bit of a bully, wasn't he? I mean, he caused that his rival to commit suicide when he was ravished by Terzaghi. It was a real blot on Terzaghi's record, really, but he really was a very domineering person. Bishop was the opposite, but I don't doubt that if Terzaghi had been presenting something at a conference that had any holes in it, Bishop would not have hesitated to point them out. But I don't think that they would ever have sat down together. Terzaghi's visit for the Chingford Reservoir failure would have taken place before before Bishop even joined into the work that he did on it later on. So I meant to mention one thing when I was talking about Bishop and his wife Myrtle, that they were very happily married. I mean, they couldn't have been happier. They talked about all sorts of things, and Myrtle had owned a forest or something, or a piece of land up in Scotland. So during the summer, they often went up to Scotland and spent their time in that cottage. But what was really sad, I visited them in 1962. In 1968, I got a letter from Peter Vaughan or somebody telling me that Bishop had died. They had decided really that his heart was so uncertain they would operate on it. The operation apparently went successfully, but something happened in 4 or 5 days after the operation, and Bishop died. I contacted the place of of worship in Cambridge, where Bishop was part of the Quaker community. I contacted them to find if anybody knew anything about the Bishop, and one of them did recall that Bishop was a great walker, and that he had walked through the tunnel. There was a tunnel on the railway that connects Canterbury with Whitstable, and Bishop had walked through that tunnel. It was probably after the trains had stopped going through it, because they only used it for a certain length of time. And when I was doing my PhD, and Richard Pugh was there, he was doing the fieldwork, but for some reason or other, Bishop asked Richard, he probably thought I was too busy. Bishop asked Richard if he would like to come down to Canterbury, because there was a collapse affecting one of the buildings of the university there. So he went down with Bishop just to have a look at the surf effect. So some part of the old tunnel had collapsed, and as things do when mine shafts and things collapse, it had caused a little bit of damage to the buildings above. So that was that.
So interesting. It's fascinating to hear from you Laurie, about these intimate details about Bishop and what happened. Just say, have we got Trevor Symes online? Is he? No, I think that the question from Trevor isn't coming. Any other last chance? Yeah, Phil, would you like to ask a question?
Yeah, thanks, Laurie. I do have one question, and I'm reflecting on your comments about when to use drained and undrained analysis. So when I hike around Indonesia, I see rice paddies which are clearly very steep and totally saturated. And I don't think I can explain why they're so stable. And I'm sure if we designed one in Golda, they would end up being an awful lot shallower than what I see in the field. Can you offer a way as to how I could analyze those? And unfortunately,
No,
I can't find a client who would pay for it though, sorry.
No, I did enough research into allophane clays or allophane and doloysite clays. In fact, one thing I did when I did my PhD, I took a sample of an allophane clay to London because I wanted to get a measure of its residual strength. Actually, the tests I have done, I can send you a paper. The tests I have done come up with the surprising fact that the friction angle for allophane clays is almost approaching 40 degrees. In other words, it's out on its own as an extraordinary piece of behavior, especially as the allophane particles are about 100 times smaller than the normal kaolinite or montmorillonites. They are very tiny particles, but for some strange region, their peak phi value is approaching 40 degrees, and it hardly deteriorates if you measure the residual value. I must have known that Bishop had a ring shear apparatus for measuring the residual strength, so I took the opportunity to measure the residual angle of the allophane clays, and I was astonished to find it was so high. But other people have done similar tests since, so it's gotten an friction answer to your question. Yeah, I wondered when I first went to Indonesia. In fact, I always intended to do a bit more stability analysis. I did one time start drawing flow nets just by hand of the way the water went down there, and I was always a bit puzzled because it's not, water doesn't just enter from each level. Water also comes out to some extent on each level. That's the only way the seepage pattern makes sense. I eventually got around to finding time to use the CW bow-gun and check it out, and it came out with the same pattern. But that's the answer to your question, that for allophane clays are very unique clays. They get natural water contents up to 150, 200, something like that. Liquid limits up to about 250. I know one time one of your local engineers told me that his laboratory had done Atterberg tests and other tests for some American consultant. And when he wrote his report and put all the values for the allophane clay, and the Americans told him, "You've got a mistake here, you can't possibly have soils with water contents as high as that." So he told me that as an interesting reflection on the fact that sort of amongst most people, it's extraordinary to have a clay with to stay stable on banks, and the way you observe, they're amazing because they're fully saturated, and the slope at the front is never quite vertical. I mean, they look as if you're cutting them vertical, but they're not quite vertical, which is another interesting general point, that vertical banks in clay are a recipe for disaster because they'll fail. But if you cut them at about 75 degrees, they are far less likely to fail. It's just a situation where theory no longer applies. You can use theory to calculate the safe height of the clay bank, and you'll come out with a height which was just a recipe for a disaster, really. The people who regulate trench work, they limit the height of the depth of a trench, some 1.2 meters, others 1.5 meters. But the reality is you can't rely on formulas from textbooks to estimate the safe height of vertical banks, particularly in trenches. If it's just a vertical bank by itself and it slips, it might push you sideways. But if you're working in a trench and the thing collapses, it pins you there and you're a goner. There's no way you'll get out before you die from suffocation. Anyhow, we don't. Enough of that.
No, thanks, Laurie. Yeah, I think some good lessons there. I think there are no other questions in the room, and we can't quite get one from one of our colleagues. So I think probably, Laurie, we can thank you very much again for covering such important information so thoroughly. And probably we can let you go and have some sleep. We're going to see if anyone's got questions for Stephen from earlier on. I'm not sure. That's going to be the last chance, unless you've got one yourself. But I mean, he made a presentation which involved some of the principles that you were talking about, in fact. So is there one or two questions for Stephen anyone would like to ask?
I'd like to ask a question.
Yes, please.
They were building a new metro railway line in Jakarta the last time I was there. Has that been completed, and is it operational? Or?
Railway line to the airport?
Oh, I thought it was sort of going north and south right through the main way through Jakarta up towards Kota and right down to Kebayoran or something.
A railway line? Well, no. Oh, we have the underground. We have the MRT. Yes. Yeah.
That's what I was wondering.
Oh, correct. We have half a line. Yes.
Oh, good.
Yeah. Because it starts in the south and it finishes in the middle.
Does it? Right.
And they just started to build the section going north. So it starts at the Welcome Roundabout, which I'm sure you remember.
Oh, yeah.
So by the Hotel Indonesia, although it's changed its name. So that's where it stopped. Yeah. And it comes up from the south. Correct. Yeah. Well, and it's very good. So hopefully when you come here, you'll be able to use it. It's very good indeed.
Oh, good. I must come and visit Jakarta again. So
you're most welcome. Most welcome, Laurie. We hope you'll come to see us again. Certainly now that COVID is rather simpler to deal with, it's a good time to come. So
excellent. Greetings to Sandra too.
Yeah, she's waving. Right. So and I think probably looking at the time, it'll be a good time to bring this this event to an end. I'd like to thank you one more time, Laurie, for putting in so much effort on that explanation of the background to this important thing, especially some of the insights into these incredibly important names, Terzaghi and Bishop. I mean, two of the major names of soil mechanics, and by now people take for granted what they established. Although I have to say, many people need to read the 1960 paper to learn how to apply the strength values correctly, because we see so much poor use of strength data from the incorrect type of strength testing. And it's really quite disappointing. They simply haven't understood the importance of those two fundamentals about the effective stress side and the total stress side and the differences. So thank you again for emphasizing that. We'd like to circulate a PDF copy of your slides, if we may, to people who take part. So I'll get in touch with you about that tomorrow by email. And apart from that, unless any other last comments, I shall bring my part to an end. I'll just be asking our MC to say a few final words, and then Laurie, you can return to your sleep, I hope. But thank you again very much.
It's a pleasure. It's very enjoyable. Nice to meet you all and talk to you.
So Laurie, can you close the share screen, please? Okay. Very nice of Mr. Laurie. Okay, everyone. Thank you, Mike Dobie and Phil Mancy for guiding the session. Once again, thank you for Laurie Wesley for your excellent presentation. And also thank you for our featured speaker, Stephen Christian. Ladies and gentlemen, we have now reached the end of the event. Once again, thank you for your participation. We hope to see you at the next event. At least, good evening and stay healthy, everyone. Thank you.
I will say farewell too and close this down.
Yeah. I think just switch off, Laurie.